Hello everyone. Today I am here to discuss on the topic area vector, electric flux and Gauss's theorem. So to understand what is Gauss's theorem, we need to know what is area vector and electric flux. So let us see first what is area vector. So let us see first this topic. Suppose you draw an area given by this and it is of area ds and it is a two-dimensional area, planar area, then its area vector will be along this direction. So this is known as the area vector. Now this vector is always along the outward normal. If this is your plane, it will be in perpendicular direction along the outward normal to the plane. So now this ds vector can also be written as ds n unit vector, where n is a unit vector along the outward normal. Okay, so we can write a vector in this form also, its magnitude, and beside it we can write the unit vector. Like if we remember, like if a vector, we can write it also as a I cap vector. Then what is the meaning of this? Like the vector a has a magnitude a in which direction? In the x direction. Okay, so if we take this example and compare it with this, so we can understand why it is written ds vector equals to ds n cap unit vector. Okay, now if it is in this form, if an area is in this form, how can we represent the area? So area vector, sorry. So in this case, how we can represent? We can divide it into segments and suppose we take a small portion, suppose, and let it be of area ds. Let it be of area ds and it will have a normal ds in this manner. Okay. So in case of a curved surface, we can take a planar area in this form and we can represent its area vector in this manner. So this was about area vector. Now let us see what is electric flux. So we have discussed this one. Now electric flux. So electric flux is the number of, or the total number of electric lines of force passing an area normally. Suppose this is your area. Okay, you have taken an area. A planar area is this, and electric field lines are passing in this manner through it. Electric lines of force are passing in this manner through it. Then electric flux will be given by, there is a formula of electric flux where flux through a small area is given by dot product of E dot ds. Suppose you take a small portion of this. Okay, at first suppose you take a small portion and you see how much flux is passing, how much electric lines of force are passing through this small area. Okay, suppose this is ds. Okay, how many electric lines of force are passing through this area? So d phi, small phi, will be dot product of E dot ds, and since it is the dot product of two vectors, one is electric field vector, another is area vector. So since we have learned in class 11 the dot product of two vectors gives us a scalar quantity, so d phi is a scalar quantity. And if you want to find out the total flux through this surface, okay, so how to find out? You have to take an integration of E dot ds, or you can write in this manner first, d phi, okay, you can write it d phi, and then you can find out, you can write E ds cos theta. In this manner you can find out the total flux through an area. Okay, now in this case the electric field lines of force are perpendicular, okay, are normal to the surface. Now suppose if it is not normal, suppose this is your surface and your electric lines of force are passing in this manner. So in this case what you have to do, you have to take the normal component of, suppose this is, we are considering suppose this line, so you have to take the normal component of, so if this is your electric field, so you have to take, let us erase it for now, you have to take the normal component of this field in this direction, and if this angle is theta, it will be E cos theta. Okay, so in this case we can understand that why do we write in this manner, d phi equals to E ds cos theta, or E cos theta dot ds, that is the product of normal component of electric field to area. So whenever there is an angle theta, then we can write it in this manner, and we can mark it as n unit vector. So we can say n unit vector is the direction normal to the direction along the outward normal to the surface. So this is how we can represent a flux. This is electric flux. Okay, so this is your electric flux. Now, what is the unit of electric flux? So here it is the product of electric field and area. So we can write its unit is Newton per Coulomb, is a unit, into meter square. Okay, you can write in this manner, this is the unit of electric field and this is meter square is the unit of area. Now, okay, another thing, whenever you will write the total flux, you will put a closed integration. That means you take the integration over a closed surface. That is the total number of electric field lines passing through a closed surface. Okay, so now we shall discuss about Gauss's theorem. So electric flux we should know before understanding Gauss's theorem. That's why I taught you electric flux before Gauss's theorem. Another thing, phi is or electric flux, the mathematical name is phi. So in physics we name it as electric flux, and it is a scalar quantity as I had already mentioned. Now, what is the meaning, what does Gauss's theorem state? So Gauss's theorem states that the total flux through a closed surface, is 1 by epsilon naught times the net charge enclosed by the closed surface. Now, what does it mean? So this is a Gaussian surface we have drawn. This surface is known as Gaussian surface. So it is any hypothetical surface enclosing a charge, and we can say that it is an imaginary surface. It does not actually exist, but we draw it, okay, and we draw it mainly to find the electric field due to a system of charges or symmetrical continuous distribution of charges. So this is done for this reason. Now this need not be always circular. It may be of other shape also, but this Gaussian surface should be a closed surface. Okay, so the number of electric field lines or electric lines of force, or we can say the total flux passing through this closed surface is 1 by epsilon naught times 1 by epsilon naught is this, and this you know is known as permittivity of free space. 1 by epsilon naught times the net charge enclosed by the surface. So this surface encloses a charge Q. So that's why here we have written Q as the net charge. So this is the net charge enclosed by this surface. Okay, so now we can write this as, we have already written it as, we have already learned that phi is closed integration of E dot ds vector. So here from phi we write it in this manner, Q by epsilon naught. So we can write this as the main formula. And if you want to represent it in the diagram, how to write it? Suppose you consider this much area, okay, and this area vector is in this direction. Now since this is a point charge, electric field lines are radial, okay, electric lines of force are radial. So you will also have an electric line of force along this line only, okay. So then we can say this E and ds are in the same direction since this is a point charge, okay, and this area can be represented in this manner. We consider this area ds and it will be represented in this manner in the form of a cone, okay. So this is, and if this has the total area of this sphere is S, and we take small area on the surface, and this small area has an area vector in this direction, that is perpendicular or outward normal to this surface, and electric field also due to a point charge is along the outward normal, is along the radius. So these two will make an angle 0 degree. So in this case, if you had to calculate phi, d phi E dot ds, or we can write it as E ds cos theta, so it would have been E ds cos 0 degree. That means E ds, okay. Since your theta equals to 0 and cos 0 equals to 1, so in this case phi d phi would have been E dot ds, okay. So your main Gauss's theorem is this. It comes from this, phi equals to 1 by epsilon naught times q, and suppose for this sphere if we had to find out, so we could have found out in this manner. So E dot ds will give us integration E ds equals to q by epsilon naught, or let us erase this whole portion. phi equals to q by epsilon naught, and this is also q by epsilon naught. If we had to find out for this particular case, so we can easily find out E ds q by epsilon naught, since in this case theta is equals to 0 degree. So E will come out ds epsilon naught and ds. So this is the small portion area of this sphere. And what will be the total area of the sphere? It will be into 4 pi r square q by epsilon naught. Therefore E equals to 1 by 4 pi epsilon naught q by r square. If we arrange it, we will get this. That means it is the electric field that we get due to a point charge. Okay. So, and it will be directed away from the charge along the radius. Okay, along all the radial direction it will be pointing. Okay. So that's all. And if suppose we say that suppose we bring a test charge sitting in this portion. Suppose we bring a test charge and say it is sitting in this portion. So what will be the force due to this test charge? So we can write force as E by Q naught. Q naught into E. That will be Q naught into E. So we know it is 1 by 4 pi epsilon naught Q by r square. So already one Q naught is here. So Q naught by r square. So this is your force. Okay, and hence Coulomb's law is also proved. Okay, so here what we did, we explained how to get force, Coulomb force from this Gauss's theorem. Okay, so we can easily prove the formula of force from Gauss's theorem, and it is very easy, as you can see. And this force will also be a repulsive one because we have taken this as positive charge, and here if you imagine there is a charge Q naught sitting at this distance r. So at this distance r, okay, so we can then write it in this manner, and it will be away from, means it will be along this direction, away from the charge Q. So that's all for today. Thank you.